basis for null A. And so what we're looking for is AX equals 0. That's the null. And what we do is we take that, and in the problem, they've given you a echelon form of A. So we'll just start with that echelon form of A. So that's 1 minus 2, 9, 5, 4. Now what we want to do is we want to get this into reduced echelon form. And we're going to start at the bottom and work up. Now, you understand that we're actually looking at this as an augmented matrix, right? I'm not going to put that augmentation in there. The augmentation is this 0. I'm going to put it in at the end, but not now. So now this next row, we don't have to do anything with that, because 0 is why we have to do something with it. I'm going to multiply a number times 2 to get. I really don't even have to know what I multiply. I just multiply. I'm actually multiplying by 7/2, right? Minus 7/2, but it doesn't make any difference. That goes to 0. One minus 2, 9. And now then I have got to multiply that by need to think about this. I did this wrong because there's a 0 right here. I don't multiply anything by this 1 to eliminate anything up there. So this remains a minus 7. Okay, now I got to get rid of this 5. So I multiply the second row by minus 5, makes this 0, and then minus 5 is a plus 10, and this is 14. Now, the next one I can work on is this one right here, right? I can't do anything with any of those others. So now I'm going to multiply the second row by 2 and add it up. So it's 1, 0. That's a minus 6, 3. This is 0. And then that's 0, right? And then I go 0, 1, 0 minus 7. Now what this is an augment, so technically what I have is zeros up here. And then if I write this in parametric form, this first row says that x1 plus 3x3 equals 0, correct? Second row says x2 minus 3x3 minus 7x5 equals 0. Now, x3 is free. And then x4 plus 2x5 equals 0. And x5 is free. So I can solve this. x1 equals a negative 3x3. x2 equals 3x3 plus 7x5. x3 is going to equal x3, whatever it is. And then x4 equals, that's 2x5, right? And x5 equals x5. I can do this. I can do this x3 times the matrix, the vector, minus 3, 3, 1, 0, and 0. Let's go ahead. And then it's plus x5 it's going to be it's a 0. This is a 7, isn't it? 0, 2, and 1. So then the basis for null A are the vectors minus 3, 3, 1, 0, 0, and 0, 7, 0, 2, 1. says. And the dimension of column A, there were 4, right? No, 3. We had 3, we have we had 3 turning points, or pivot points. This one, and this one. That means the dimension, or those vectors in the original A are the basis for column A. So its dimension is 3. And then the dimension for null A is 2. These 2 right here. And I did that. I did the basis for column A, and that was the vectors in the first column, second column, and the fourth column. Those are the basis for column A. And the dimension of it is 3. Do another one like this. 12. So it's 1, 5, 4, and minus 2. 2, 10, 8, and minus 4. Minus 4, minus 9, minus 9, and 5. 3, minus 7, 3, 7, so then count this 1, 0, 0, 2, for a pivot here, there, and there. So then when we do, they're asking us for find the basis for column A. And it's going to be this vector, and this vector. It's 1, 5, 4, and minus 2. It's going to be in the original matrix, it's going to be the columns that contain the pivots. Minus 4, minus 9. And then the dimension of column A equals 3, because its basis has 3 vectors. So you can see that you're going to have 2 free variables. So the dimension of the null A is going to be 2. Because if you look back, the rank and the dimension are the same, and in Theorem 14 it says if the matrix A has n columns, then the rank of A plus the dimension of null equals n. So there are 5 columns. Dimension of column A is 3, so therefore the dimension of null A is going to be 2. And you're going to have 2 free variables, and they're going to be 2 and 4 in this case. But in order to figure out what the vectors are in the null A, you have got to get it in parametric equation form. So you're going to have to go on from here. And you got to start from the bottom. 0, 0, 0, 0, 0. And what we're doing is we're augmenting this thing. So we got another column of zeros. 0, 0, 0, 0, minus 5. Now, this is what I could do at this point, is I could augment this thing. So that I could write this thing down here. As 1 with my augmentation. That way it makes it easier when you go up here. 0, 0, 1, minus 2, 0, and then my augment. And I go 1, 2, minus 4, 3, and 0 with my augmentation. And now I got to go to my third column and work on that first row. 1, 2, and I take the second row times 4 to make this 0. That was a 3, wasn't it? So I'm taking the second row times 4. That's 8 minus 8 plus 3 is a minus 5. 0, 0, 1. I write my parametric form. This says x1 plus 2x2 plus, no, minus 5x4 equals 0. So this is my augmented thing, so this is going to be these values, these 0 are there. Then my second row says x3 minus 2x4 equals 0. And my third one says x5 equals 0. So x1 equals a minus 2x2 plus 5x4. And x2 equals 3. So I can just put x2, x3 equals 2x4 x4 is a 3, so it equals x4, and then x5 equals 0. So then if I take x2 and its vector is a minus 2, 1, 0. Move this over. 0, 0. Plus x4, and that's 5, 0, 2, 1, 0. You could write x5 is zeros, but it means nothing. So then the basis for null A is minus 2, 1, 0, 0, and 5, 0, 2, 1. Those are the basis vectors, and the dimension of null A equals 2. And notice that the dimension of null A plus the dimension of column A equals the number of vectors in A. That's a way. It's easy to find the basis for column A, but basis for null A, you got to get that. In the reduced form. So any questions on those? The instruction says find a basis for subspace spanned by a given vectors. What is the dimension of the subspace? Now, notice it says a basis. It isn't going to be, all of the bases, but it's going to be one of the bases. So you take your vectors and put them in a matrix. So 1. Now, the basis is some of these vectors. So in order to figure out which vectors it is, you have to put it into a matrix. And then you want to start going towards an echelon form of that. So I'm going to multiply the first one by 1 and add it. Minus 1, 2, 3, minus 5. I multiply the first one by 2 and add it. 0, 3, minus 6. The first one by 5 and subtract the first one by minus 5. 0, and minus 4, 8. That's 12. Minus 10. Okay, did I make a mistake? You shouldn't tell me. One, 2, 0, minus 1, 3. Then I'm going to divide that second row by minus 1 because that will give me my diagonal to plus 5. I better put this down otherwise I'm going to get working on the second column. So I'm going to multiply the second row by minus 3 and 8. 0, 0, 0, 0. And multiply it by 4, 0, 0, 0. That's 20. This is 10. I think I did something wrong. It has to be back when I did this one. Did to get ready here. So I multiplied the first row by 4. First row by 4. Where in the heck is the error? I think that should be minus 20. Just clear back up when it's clear back. It's back up here. I'm taking, that's back here. When I'm taking this one times, it's like a negative, times a minus 5. Okay, it's this thing here has got to be a negative. That's what error is. My original problem. Then that makes this one a minus 20. It's this one. And then this makes this one 0. Okay. So now what we do, all they're asking us for, 14, is find a basis for the subspace spanned by the given vectors. So it's going to be the same as the basis for column A. And because our pivots are here and here, that means this original vector, this basis. Basis for column A is A basis a subspace. Span by a given set of vectors. And those vectors are those two. So vectors are 1, minus 1, minus 2, and 5. And 2, minus 3, minus 1, and 6. And then it says, what else? What is the dimension of the subspace? So the dimension of subspace is equal to dimension column A, which is 2. So, is that 16 says, suppose a 4 by 7 matrix A has 3 pivot columns. Is the column A in R3? So A is 4 by 7. So what you have is you have 1, 3, 4 elements in each vector, and then you got 7. So this is a 4, 7, and then you got 4 along here, 7 along there. Now, it has 3 pivots. So 3 of these vectors, which have 4 rows, that are 4 by 1, are in the column, are in basis for column A. That means they are in R4. And it says A, therefore A cannot, the column A cannot be in R3 because there's more entries in each vector than 3. There's 4. So they have to be in R4 space. And then the dimension of null A is equal to 7 minus 2, because there's 2, the dimension of column A is 2, so the null A is going to be 5. Because if you look at theorem 14, says a matrix A has n columns, then the rank of a rank dimension, whatever it is, plus the dimension null A has to equal n. It has to equal the number of vectors, and the number of vectors are 7. So in this particular matrix, there are 5 free variables. So when you go to do the parametric equation, you'd have 5 frees. It says B is the basis for the subspace H, then each vector in H can be written in only one way as a linear combination of the vectors in B. So if you look back on page 155, and then you look where it says coordinate systems and look in that first paragraph. And it says the main reason for selecting basis for a subspace H instead of merely spanning a set is that each vector in H can be written in only one way. And that's, therefore, that statement is true because that's what it's telling you right there. Right? True. That's page 155. The B there says that if B, the basis B is V1 through BP, is a basis for the subspace H in Rn, then the correspondence X mapped into X basis makes H look like and act the same as RP. And that's got to be true. If you look at 157, second paragraph, in general, if the basis is B1 through BP is the basis of H, then the mapping X into X basis is a one-to-one correspondent that makes H look exactly like RP. There's the statement right there for that. C, so this is page 157. And this one says the dimension of null A is the number of variables in the equation AX equals 0. So if you look on page 1, if you look on example 2, the dimension of the null A is the number of free variables in the equation AX equal B. That's example 2. And that's where it tells you that. So this is false. And if you look at example 2, it will explain it. And D says the dimension of a column space A is rank A. And that's true. If you look at definition of rank, page 157. It says the rank of a matrix A denoted by rank A is the dimension of the column space of A. E says if H is in a p-dimension subspace of Rn, then a linear independent set of p vectors in H is the basis of H. That's true. Theorem 15, page 158. Tells you right there. And it's just that theorem. Okay. 20. It says, what is the rank of a 4 by 5 matrix? So the matrix is 4 by 5, whose null space is 3-dimensional. So then the dimension of the null of A equals 3. And if you look at theorem 14, theorem 14 says if a matrix A has n columns, then the rank A plus the dimension A equals n. So this thing has 5 columns. A has 5 columns. And rank A plus dimension of null A must equal 5. Therefore, rank A plus 3 equals 5. Rank A equals 2. And this was theorem 14, page 158. Okay. I guess that's all problems I'm going to do. So there aren't 20 questions. Seems like to me like I can't remember how many there are. When I skipped one section in this, right? 2-8? 2-7. So there's 8. I'm thinking there's probably around 16 questions. I took 2 from each section. Well, this test is over all of it. I think the first test I gave over 1. So this is just everything on 2. They're odd problems out of the text, and they're not, I'm not going to do very difficult problems. And the thing is if you have on the test, when you're taking the test, if you have a question about something or you don't remember maybe a theorem or a definition, be sure and ask me, because don't you assume that I won't tell you. Let me make the decision. And then if I do tell you what it is, I'll tell the class what I told you, so that everybody has the same benefit. I told you about the final, right? a third off each one of the columns.